All right, so let's take a look at today's lesson. So today's lesson is really kind of going more in depth about accumulation functions. We talked about accumulation functions last time, and so we're just going to continue to talk about that topic, and we're going to also talk about some specific properties of definite integrals. So first, let's remind ourselves about the accumulation. This is usually how the accumulation looks right here. So you'd have some function, they're calling it big f of x, is going to be equal to the integral from, some number typically to x of f of t. So the relationship between these two is really important. So if I integrate f, little f, and I get big F of x, then what is the relationship between little f and the big one? Very, very close. So this one is the derivative, right? This one is the derivative of this one. Really important. And I know I've said that before. I'll say it again. If that's something that you're having a hard time memorizing or remembering, you just need to memorize it because that is crucial. So, and I'm just going to write up here. So f of t is the same thing as f prime, big F prime of x. The little f is the derivative of big F. And if you remember, we looked at like part 2 of fundamental theorem of calculus, and we looked at if I took the derivative of this side, that would be the same as the derivative of this side. Remember all that we learned last time? Right? So in other words, big F prime of t would be the derivative of the integral would just, that x would plop down in there and we would have that. So that relationship is really important. Okay? We're talking about that again. Okay. So, and also it's, written right here as well. Okay, we'll just highlight that because it is a big deal. So let's look at these concepts that we're talking about increasing, decreasing, relative max, relative min. We covered that last semester, but we are still continuing to look at this now in terms of the accumulation function. So keeping this in mind, I'll just highlight, keeping this in mind that big F prime is the same as little f of x, we would know that big F of x is increasing when f prime of x is greater than 0, this one, big F prime of x, or f of x is greater than 0. We would be able to look at either one of those scenarios and be able to determine whether the function is increasing or not. If the function is decreasing, we would see that by looking at its derivative. So its derivative would be negative, and whichever form we see it in as big F prime of x or little f of x would be negative. Okay, so that's something that we have looked at before. Relative minimum and relative maximum. If you recall, for the relative maximum, then this derivative would change signs, right? Would change from, for max, it would go from increasing to decreasing, right? So it would change from positive to negative. And little f, which is the same thing as big F prime, would change from positive to negative. Okay, which is actually the first derivative test. Somebody, at least one, no, 3 or 4 people in here had that on their formula quiz, the first derivative test for relative extrema. That's this. Relative min would be if the derivative changes from negative to positive, whichever form we see the derivative in, which at little f could also, which is also the derivative, changes from negative to positive. Concave up. Do we remember how to determine concavity? Which derivative do we look at for concavity? We look at the second derivative. So this one would look like this. The second derivative, concave up, would be greater than 0. This one would be f prime, right? The derivative of this would look like f prime is greater than 0. So this is a little bit of a difference in the way that they look, just like these. On the ones we were working with, this one is basically designated as big F prime, and this one is designated as just little f. And so that's the significance. When we go to second derivative for this side, we would go to first derivative for this side. So concave down would be when the second derivative is negative, or in this case, the first derivative of little f is negative. Now, inflection points, do we remember what is significant? How do we determine if we have an inflection point? Concavity changes, right? The concavity changes. Another way to think about it also is that f double prime changes sign. That would be a test to look at it. So f double prime, if I could write, f double prime of x changes signs. Or little f prime of x changes signs. Now, these are true. These two match like this if we have accumulation. Call this a definition. If we have this accumulation function defined, then these things are true. I just want to make sure we understand that. They're not true just because of, some other weird reason. They're true because of the accumulation function, the way it's written. Okay, so that's just a reminder of what we've done in the past. We're still, these concepts that we're working on aren't going to go away. They just keep, keep going in different forms. So this is another way to look at they're calling this behavior of accumulation functions. Okay? Are we good with all that? That should kind of be comfortable and familiar. Uh-huh.
I don't know if this actually is a difference, but on the quiz inflection, the last one, on the left, is that a lowercase or uppercase?
Left. This one, it's my messy writing. This one is the uppercase guy. Yeah, you bet. Okay. All right. So let's look at some examples. So this we need to pay close attention to. Okay, so this is our accumulation function. They're telling us that f, this is f right here. So that means that f is the same as g prime. That's what that means. And you really should write that on your paper. You will get credit. Actually, you will not get credit if you don't write it on your paper. I'm just saying. You have to establish that relationship before you can justify things. So really important to write it down. All right, so since this is a derivative graph, and I know y'all have seen me do this before, I'm going to do a sign chart on it because that just helps me with my thinking. Do you have to? No, you don't have to do a sign chart, but I'm going to because, again, it just helps me with my thinking. So this is g prime. And g prime from, on this side, this is positive. It's positive, right? And right in here up to, that's 5, I don't know, like 5.4 or something. That's negative, and that's positive. Okay, so that's just going to happen. And this, I'm just going to label. This is g prime. So that's a sign chart for g prime because they're getting ready to ask us questions. And in order to answer these questions, it's going to be important that we can interpret what the graph is doing. So the first question that they ask is, and they want us just to find the x values. They want us to find a relative minimum of g. So to determine what's going on with g, we look at g prime. And if you recall, right, relative minimum would be where we're changing from, decreasing to increasing. There would be a relative minimum, and I'm just going to have to approximate that. We're just going to call it, I don't know, about 5.4. That's where a relative minimum would be. And let's write our justification. Even if they don't ask, it would be wise to write a justification. Because why? Why do I know that? Why do I know that's a relative minimum? Because G prime changes from negative to positive. Okay, so let's just get used to writing justifications, even if it doesn't ask. G prime changes from negative to positive. Relative maximum of G. Okay, so that's where we're looking for G to go from positive to negative. So we can see there's a relative maximum at x equals 3 because G prime changes from positive to negative. Now concavity is where we're looking at the second derivative, right? G double prime. I don't have, let's just go ahead and do another sign chart for the second derivative. I'm going to put this up here. So we're going to just call this G double prime. Okay, so how do I read the second derivative off of a first derivative graph? What am I going to be looking at? Slopes. I'm looking at slopes. So this slope from here, I mean, that slope is like 0, right? The slope is 0. So that's weird, but it's a thing. It's okay. So let's see. We go to here and we see that slope is negative. And to here, we see that slope is positive. And then we go back to a 0 slope. All right, so as we look at that, the intervals where G is concave up, that would be where G double prime is positive, right? So let's write down that interval. That would be what, 4 to 6. Now, since we have a graph of G prime, instead of saying because G double prime is positive, which we really want to say, instead we have to say because, and we've got caught by this before, if you recall, because G prime is increasing. We need to really specifically talk about the graph we're looking at instead of, what we did. I know what we did was correct. We do read it from the slopes, but it's cleaner to just talk about what that graph is doing. That graph is increasing, and also G double prime is positive. Are we okay? Okay. So we want now to know, where is G concave down? Again, G is going to be concave down when G double prime is negative. That's a lot to memorize, isn't it? And if you get it mixed up, it's just not good. So hopefully those things are starting to solidify in your brain. That's a thing, right? G is concave down on the interval from, where are we? From 2 to 4, because G prime is decreasing. And the reason we have to write it that way is because of the graph. Does that make sense? I mean, I really would like to say, and I'll put this in parentheses, I really would like to say because G double prime is less than 0. I mean, that's much shorter to write than all this. But we're really required to talk about the graph that we can see. Okay? Points of inflection. And we talked about that. Y'all told me, actually, is where concavity changes. Now, let's talk about this 0 business. Is there any concavity right here with a slope of 0? No, there's not. So I don't have a concavity change at 2 because I've got no concavity to concave down. I just want to make sure we understand. No concavity to concave down. That's not a concavity change. The concavity change is at 4, right? It's at 4. So we would say x equals 4 because, and we've got to go by the graph. What I want to say is because G double prime changes signs. That's what I want to say. But what am I going to have to say? Because G prime changes from decreasing to increasing. That's what I'm going to have to say. Even though I would prefer to say the other, I can't. Because G prime changes from decrease to increase. Okay, we're doing great. The last one is asking us, they're telling us, well, that's interesting. They're telling us a position of G. They're giving us a point on G. And they want us to say, what is the maximum value of G? So just so we remember, maximum value is a Y value. It's not an X value. Maximum value means Y value. And they gave us an initial condition. So what are we going to have to do? Okay, what we're going to have to do is, let's look at where it is first. What X value did we say was a maximum? We said it was at 3, didn't we? It's at 3. So here's how we need to find out what the Y value is. So I take the original Y value at 1, 5 plus, and I want to integrate from 1 to 3 of f of t. Now, when I find area under the curve of a derivative, we've done this before, it gives us a position value. Remember when we were, let me just remind you, for this lesson back here, remember when we were accumulating as we went? Remember that? How we accumulated and we found out these are Y values right here. We found Y values by finding area under the curve of the derivative. Remember that? That's what we're doing here. We are finding right here. We're going to calculate what this Y value is by starting with the Y value that they gave us, which is 5. And notice, this is significant, that this is G of 1 and this is 1. That is significant. Those have to match.
Where'd you get the 3 from?
The 3 came from knowing that 3 is where the relative maximum is. Yeah, that's why I picked 3, because that's where it is. And they want me to find the Y value of where it is. Does that make sense? They want the Y value of where it is. So that's what I'm working on, is the Y value of where it is. Are we good? Okay. So now to see what accumulated between 1 and 3, we're going to have to actually, calculate the area between 1 and 3. So let's do that. So we're looking at this we're trying to calculate all of this, right? That's what we're doing. We're calculating the area between 1 and 3. So let's see, that's 2, right? Those 2 blocks. And this would be half base times height, half 1 times 2. This would be 1, right? So this area is 3. Are we okay with that? I'm just finding the area between, that rectangle and the triangle. So I've got 5 plus 3, and that's 8. So the max value is 8. Okay. We good? Okay, let's look at a weird one. And y'all are like, that one already was weird. Okay, this is a different weird one. Let's look at number 2. It says, let G equal, okay, so I need to get this bigger. Are we all good? We've got that copied down? Okay. Let G equal the integral from 0 to x over 2 plus 5 of f of t dt, where the graph of f is shown below. So this f of t, we'll just say f of x, is g prime of x. Okay, that's the relationship. Write the relationship down very first thing so you don't forget. Write the relationship down. So this is the derivative of g. Okay, they want us to find the place where there's a relative maximum. So let's do that first. The location, because we're going to have to mess with this in just a second, but let's do the location. So where would g have a relative maximum? That would be when g prime changes from where we got maximum, so positive to negative. And this is g prime, right? This is a picture of g prime. So where does it change from positive to negative? At 3, right? This is where it changes from positive to negative. That's the x value if we didn't have this weirdness going on with that weirdness. So let's set up our equation so we can figure out what the actual x is. I know that's the x, and if this were just x, it would be 3, but it's not. So what do we do? So g prime of x is equal to f of, so what do? We take the derivative. Let's just remind ourselves of our rule. If I take the derivative of this side, I have to take the derivative of this side. I'm just reminding us of our rule. Remember? And the derivative of the integral, remember that we learned, the fundamental theorem part 2? What are we supposed to do with this thing right here? This thing, where's that supposed to go? Yep, it's supposed to plug in right here. And if it's something other than an x, or just, I mean, we have to chain it, right? We got to chain it. So g prime is going to be, that's going to stick there. So it's going to be f of x over 2 plus 5, but I have to chain it.
Why aren't you doing the derivative?
The derivative.
Oh.
Yeah, I'm doing the derivative of both sides. The derivative of g would be g prime. And then the derivative of the integral is that fundamental theorem part 2 where we take that bound and we stick it in there and then we chain it. Remember? Are we okay?
Yeah.
Okay. So I put that in there and I chain it. So the derivative of x over 2 plus 5 is 1/2. Right? And so what I need to calculate. I need some calculations. What I need to do is I'm looking for this. I need to find out that value. Okay, that's my goal, is to find out what x is. So what do?
Wait, where'd you get the 1/2?
I chained the x over 2 plus 5.
Oh.
Right? So if we're doing the fundamental theorem part 2 and we plug something in that's just anything but a plain x, we have to multiply by the derivative of it. Okay, are we good? Okay. So I know that that is where we're looking for an equation. Okay, this will equal 0 because see, it's right here. That's when we have a relative max or min, when at a critical number, right? A critical number is where the derivative is 0 or undefined. Okay, see how everything is just coming together? Everything that you've ever learned is all right here. Okay, so let's work on, what we're going to do is we're going to work on solving this. Okay, we can do that. So I multiply both sides by 2, and I get f of x over 2 plus 5 equals 0. So what I'm wanting to know, again, I'm trying to solve for what x is. Okay, that's what I want to know. All right, so what do I do? So f of that is 0. It's kind of like, oh, I can bring up trig. You know I love trig so much. Remember when, I'm just going to do an aside over here. Remember when we did like sine of x is, I don't know, pi over 2. Remember that? Sine of x is pi, or sine of pi over 2. Hold on. Arc sine of what is pi over 2? Remember that would be here, would be 1. So arcsine of 1 is pi over 2. And remember, let's do it this way. Okay. So remember we have to figure out what angle measure would make that true, right? What angle measure would make this true? Like pi over 2, 3 pi over 2, so on. Remember when we did like this, x plus 3 equals 1? Remember what we did? Are y'all like, no, you've lost your mind? No, we don't remember. Remember how we would cover this up and we would say, where is sine 1? Okay, sine is 1 at pi over 2, and then we would say x plus 3 equals pi over 2, and then solve for x. You're like, no, that did not. Okay, so, oh, my lovely trick. I'm so sorry they forgot about you. I am so sorry, but that's okay. But not everybody. I'm sure maybe 2 people remember. Maybe? Solving? No? Oh, okay, that's okay. I'll be okay. It's going to be fine. I'm just trying to. So this right here is an example. I know. Of what we're going to do right here. I was trying to tie it to something that you know, but that failed because I guess we don't remember. But that's okay. Right? It's okay. So how are we going to do this? We're going to set this inside part. So where was G prime 0? Where was G prime 0? At 3. You with me? Where was G prime 0? G prime was 0 at 3. So x over 2 plus 5 equals 3. Okay, that's like that, which y'all are like, we don't care. Okay, it's fine. So now I solve for x. I move the 5 over, that gives me a negative 2. I multiply both sides by 2, and I get negative 4. That is highly abstract. Are we okay? You're like, sure, let me think about it. Okay, that's all right. Let's go. So that's topic 1. Okay, this next topic is, I know you don't want it to go faster, but it will go faster. So the next topic, so what are our 2 topics? Behavior of accumulation functions. We just investigated all kinds of behaviors of accumulation functions. Now we're going to look at properties of definite integrals. So these are more rules, yay. We talked about this briefly, that I could actually change the order of my bounds, the order that I integrate, by doing the minus. Okay, that's really significant for us. We're going to use it in just a minute. So that's the thing. I can change the order of the bounds by doing, this opposite thing. And we've done this already in the last class, if I integrate from like 0 to 0, I get 0. Or if I integrate from 2 to 2, I get 0. I get 0. This is called the 0 width interval. For integration, I am allowed to, if there's like this k would be a constant, I could pull it out in front of the integral if I want to. These are rules that we don't have a lot of rules for integrals. These are just, this is it, basically. I can split my integral if I'm adding or subtracting. I am allowed to split it up if I would like. If that's something you want to do, you're able to. You are not allowed to split multiplication. Let's just write that in big letters right here. And I say it now. I hope you don't forget. Not allowed to split multiplication. Or division. No. Only adding and subtracting. Because I promise you, students really want to do that, and it's not a thing. The last thing, additivity, is, and we will encounter this in just a moment. So if, let's do a number line right here. Okay. Let's say that's A, that's B, and that's C. Basically what that's saying is that if I want to integrate from A to C, I am allowed to split it. Like if I want to integrate from, would do A to B, and then I would add to that B to C. That's an okay thing to do. That's an okay thing to do. That's all this is telling you, is that you are allowed to do that. You can split like in the middle, or not even in the middle, somewhere inside the interval. Okay, are we okay? All right. So these. First of all, I want you to notice that these are upside down. Stay with me. Stay with me. These are upside down. So I either need to use the rule to change it, or I have to integrate backwards. I would recommend that you use the rule to change it instead of integrating backwards. Okay? So let's use the rule to change it. So this is going to be the same as negative integral 6 to 7 of f of x dx. So here I am, 6 to 7. I'm looking at this right here. And it's 2. So it's negative, really negative 1 times 2. So my answer is negative 2. Bless you. So I need us to understand the significance of this. If I left it like it was from 7 to 6 and I integrated backwards, if I integrated backwards, everything is opposite as it seems. Instead of this being above, I would need it above the x-axis. I would need to think about it as below the x-axis. You see how it can get really confusing? So I would recommend that you just rewrite it so that you don't have to. I mean, you don't have to. You can just integrate backwards if you want to. All right, the next one. We're going from 12 to 8. Well, that's backwards. So let's rewrite it. Negative 8 to 12 of f of x dx. Okay. So we're going from 8 to 12. Now this is all down here. Okay, I need all of that. So what is that? That's just one big triangle, right? Let's just do it as one big triangle. So, all right, so that would be 1/2 times the base is 1, 2, 3, 4, times the height is 2. So that's what, 4. Now this is underneath the x-axis. So if I'm integrating forward, which I am, then this would be, this part right here would be negative 4. But I have a negative 1 out here. So my answer is going to be 4.
Wait, where are you getting the negative 1?
Because from right here. Because we're basically multiplying by the whole integral by a negative 1 to switch the bounds. Or if I wanted to integrate backwards, I would just start here and I would integrate backwards, and everything is opposite as what it seems. It's under, so I need to think about it as over the x-axis. Okay, we good? All right. This one is abstract. And let me erase this because I need to do, this is, they love this kind where we just have, they just give us a bunch of information like, oh, okay, great. What are we going to do with all that? I've got 2 of them that are talking about F, and I've got 1 of them that is talking about G. Okay, so what do I do? This is what I like to do. What I'm going to do is I'm going to come down here, and you know how I love, I don't know, I love sign charts and number lines and all that. It makes my life easy. So I've got negative 2 right here, and I've got a 1. This is F. And then I go up to 5. It tells me that from -2 to 1, I have 4. And from 1 to 5, I have -3. Okay, that's information that's going to be helpful to me. Okay? How's it going to help me? Well, first off, they're wanting me to integrate from 5 to 1. Well, I would prefer not to integrate backwards, so I'm going to use my rule, -1 times 1 to 5 of f of x dx. And we already know what that is, right? They told us. So I have -1 times -3, and my answer is 3. Uh-huh.
Wait, why did you switch the order of the 5 and 1 on this one, but not on the last one?
Not on the last one. Which last one?
Like, oh,
Yeah, I'm going to pretty much always switch the order so that I don't get messed up. You don't have to, but if you don't, you have to remember to go backwards, and I don't want to remember that. So I pretty much always switch the order on problems like this. Let me just rephrase, on problems like this. Okay? All right, now we want to go from -2 to 5. Well, I have that written out right here, right? -2 to 5 of f. This would be the same thing as negative, well, we can even say what the answer is right now. What's the answer? 4 minus 3 is 1. Right, that's the answer. But if they wanted to see work, we would say -2 to 1 of f of x dx plus 1 to 5 of f of x dx. And that would be 4 plus, oops, 4 plus a -3 equals 1. This would be, if they're wanting work, this would be the work that you would show. Okay. Last one on this page. We're getting close. Okay, -2 to 1 of, so these are two totally different things. I don't want to keep them together. I want to use my rule, this rule right here, and I want to split them apart. Then my life will be easier. Okay, so I'm going to split them apart. So the integral from -2 to 1 of f of x plus, and I'm also going to take the 2 outside, -2 to 1 of g of x. Oops, let me put my dx there. Dx means stop. Okay. So I just used two rules there. The first rule I used was splitting it apart by adding and subtracting. The second rule I used was pulling the 2 outside, which was this one. This one is pulling the constant out. I used that rule also. Okay, so let's see what we've got. Do we have, yeah, we know what that is, right? That's 4. They gave it to us right here. That's 4. Plus 2 times. Do we know negative? Yeah, -2 to 1 of g is this one right here that they gave us. Okay, so I've got 4 plus, what is that? 16, and that's 20. Okay, how we doing? Okay, last little bit. There's one more problem to do. Does anyone need any more time on this one? Are we okay? Okay, one more little thing. Well, actually, this is 2. So I'm going to draw this piecewise function out because they want us to find this integral. Yeah, we don't know how to do it algebraically yet, which we will. I think the next lesson is algebraic, but I'm going to draw this graph out. So if x is smaller than 2, the value is 3. So we're going like this. If x is bigger than 2 and equal to 2, it's the line 4 minus x. So let's see, if I plug a 2 in here, I get what do I get? 2. And then my slope is -1. So it looks like this. Okay. They want, and this is G. They want us to find the antiderivative, or actually it's not, they want us to find the integral from 1 to 5 of G. So what am I doing? I am looking for, here's 1, looking for this to 5, and we keep going over here. And this is underneath, so I'm just going to draw that red or pink. Okay, that's what they want us to find. So that's going to be, let's see, that's 3 plus, so that's 3. This is what? That's 1, and that's 1/2, and that's 1/2. And that pink one is -1/2. And certainly there's a lot more ways to split this up than I did it. You probably have a much, better way than I do. The plus half minus half, I'm going to get rid of that. And so I've got 3, 4, I've got 4.5. So my answer is 4.5. Okay. So this is just what is different here. The only difference is I had to draw the graph of the piecewise function so I could do all that adding up stuff. Okay, one more and then we got it. So this is my graph. They want me to integrate from -2 to 4 and then absolute value it. The reason we're doing this is to show the difference between these two right here. That if you absolute value after or before, it's going to be different. Okay, so we're going to calculate this now. So this is a semicircle. What do we have? So that's 1/2 pi r squared. So r is what? 1. So that's pi over 2. Okay, so this one is underneath the x-axis, so we would consider it -pi over 2. This is above the x-axis, so we consider that pi over 2. And then we're going to 4, so this is 1, 2, this is 2. All right, so when I'm calculating this, I'm going to do -pi over 2 plus pi over 2 plus 2. And I work that out, and then so the absolute value of 2 would be 2. This answer is 2. Now, when I absolute value f before I integrate, think back to your Algebra 2 and Pre-Cal days, what is this graph going to look like? How is it going to change if I absolute value it? What's going to happen? Yeah, that thing's going to pop up, right? This thing right here is going to pop up here. It's not going to be down there anymore, right? That's not going to be down there. It's going to be up when I absolute value the graph. And so now this is going to be just a regular pi over 2. You with me? So when we absolute value the graph, there's no negative y values, right? All the y values are positive. So that means that this would flip up. So for this one, we would have pi over 2 plus pi over 2 plus 2. And let's see, pi over 2 plus pi over 2 is what, pi? So this would be pi plus 2.